Okay, hey guys, how are you? Welcome to this week 3 webinar of the Computer Vision Nanodegree program. I'm going to try to speak a bit slower this time. I know I get carried away and start speaking a bit faster, so I'm going to try to slow it down a bit. And if it's too easy for you or anything, you can just speed me up on YouTube afterwards. That's what I typically do. But okay, so the plan here today, jumping straight in, is to give you a topic walkthrough of the webinar. Um, I saw a message coming in there. It's a topic walkthrough of the project 1 of the facial key points project, detector project. I can't show you any solution code, but we're going to go through some tips. I'm going to go through some of the code, just mentioning some of the questions I've been receiving. And most of all, I'm going to start this off by giving you like a systematic view or strategy on how you can tackle machine learning projects in real life and like your real world problems that you will be working on. So how do you structure these projects? How do you work when you're moving on? How do you correct your network? How do you gauge how well you're doing, or if you're doing wrong, or which path you should take among all of the different options that exist? So that's basically what we're going to do today. I'm checking here if somebody's online. It seems to just be me for now. I checked this several times, so I uploaded several example streams earlier as well. So the sound should be okay, but please, if any of you log in and my sound, my voice is not clear, or anything else I can improve, just tell me right away and I'll fix it as we go on. So you can ask me questions on Slack, or here in the YouTube chat, which you should be able to see in one of the sides. My webcam is inverted, so yeah, it's on one of the sides, the chat. And let's jump straight in. Okay, so this time it's going to be a bit different than last time, the last 2 times. I've been working on my computer locally, showing you the basically the notebooks I've been working on. This time I'm using Colab, Google Colab, just so you can get a feel of the look it has. It's super interesting. You can use it basically just by having a Google account. And if you move up here into the runtime, and you can change the runtime type, and here you choose hardware accelerator, and you can basically none, you're just using a CPU. You can use a GPU, and if you're using TensorFlow usually, you can use a TPU as well. But so this is super useful for you guys in case you want to start working on your projects, on your own projects, or you want to keep working on the Udacity projects, but you maybe don't have any more GPU hours on your workspace, or you don't have a GPU on your computer, and you don't want to waste a lot of money just playing around with some toy projects, or as your first approach into a real world project. So you can just use Google Colab, and you have free GPU usage. It's basically unlimited, but each session is limited to 12 hours, if I'm not wrong. So you can use the same session continually for 12 hours, then it will turn itself off, and you would have to restart the kernel to get another 12 hours of GPU, and so on. Yeah, that's basically it. I'm not going to turn it on right now because I'm not going to use it, and basically the first project you don't even need a GPU necessarily, so we're just moving on here. The look and feel is a bit different, but it works very similar to how normal Jupyter notebooks work as well. So the first thing we're going to do is a quick recap on how our deep learning models work. Basically, we have this input, which can be images, text, structured data, whatever, a lot of different things. We have our model, and out on the other side we get our output. And this model, you can basically think of it as an architecture plus parameters. So the architecture is how you choose it, the way it's built, and the parameters are all these weights and biases inside of the model. And these are learned throughout the process. And the way we learn these parameters is by calculating the loss. Basically, the process here is predict, compare, and learn. So you input something into the model. This is feed forward, causing us to give us an output. We compare it to our label and generate a loss, or at least we calculate an error, because we maybe have different ways of looking at our labels. So the thing is, we use our label basically to calculate a loss, and this loss function, also called a cost function, has to be differentiable. And the reason is because by calculating the derivatives and the gradients, we can update these parameters and tell them, as I mentioned in the previous webinar last week, it's kind of a blame game. And the loss, the total loss, here usually we try to minimize this. So if the loss is high, our gradients tell each of the weights how it influenced the high loss and what it can do to reduce the loss. So basically the gradients tell each weight and bias and each parameter, please go down a little or please go up a little for next iteration. And other things, so this is something we can change around with, and that we can play around with when we create the model, which is the architecture. But other things we can change as well are the activation functions, the optimizer, the learning rates, epochs, dropout, and a lot of other hyperparameters. And we're going to talk a bit about this today. This is the reason I mention all of this. Because the types of inputs we have, the types of outputs we have, and the problem itself, it all defines how we're going to change all of these different parameters. So basically, if we have a problem, which is a binary classification problem, then we know that for our output layer, we want to have a sigmoid function, for example. Or if it's a multi-class classification, then we might want to use a softmax activation function. If we instead just want a real number, any number, and let the model just choose the number, it could be anything, a negative number, a large number, a small number, then sometimes we don't even use an activation function for the output. Instead, we just leave it as it is. But still the loss is calculated. And then, depending on how we want to train and the different types of decisions we've made, we choose different optimizers and the other learning rates, other hyperparameters. And that's something I'm going to go into a little further into the webinar. So with this in mind, I'm going to share with you guys a bit of a step-by-step on how you can tackle a machine learning project or how you can build a machine learning application in the real world. So these are basically steps. The first one is select and define a problem. And I can't stress this enough. Everything we do comes out of the problem. So if we define the problem correctly and clearly, it's basically almost automatically helps us to make all of the other decisions. But if a problem is not clearly defined, we're in big trouble. We won't even know what to do in the other problems. And this is actually something we find in industry. I mean, I've had clients coming up to me and saying, we basically want to do this, just a very broad explanation or solution. And it's not even quantifiable. We can't even measure it. We don't even know what it improves, what the benefits are. They don't even know that. So when you jump into a project and you don't even know exactly what you want, then you will end up probably wasting a lot of time, effort, and resources. The second step here is getting data. And this is not as straightforward as it sometimes might seem, because there are a lot of decisions you have to make here as well. Like, where do you get the data from? How much time do you invest into getting the data? How much data do you get? Which features do you want the data to have? Is the data biased? These are all decisions you have to take into account when you collect the data. Because, for example, if you're starting a project and basically you're thinking about what you can do and how you can collect your data, and the basic problem, and you end up thinking, okay, we maybe need 100,000 examples to train our model on this particular problem. You maybe don't have the resources to get this data. So basically, it becomes too difficult for you to do the problem. And if you can think about this from the start, it becomes much easier to make your decisions. One tip I can give you, and it's a tip that Andrew Ng also shares in his courses and in the ebooks I've shared with you guys, is often start fast and maybe dedicate 1 day, 2 days into collecting some of the data. You don't have to collect all of the data from the very start, from the outset. You can just start by calculating, okay, maybe I just need 200 examples. How much time does it take for me to get one example? If it's voice recordings, maybe 10 seconds per person. So I can go out right now and to the city center or something and start collecting data there, and dedicate 1 to 2 days and start doing something with just that data to see how difficult it is. Because sometimes we don't even know how difficult it is to get the data. So you start easy and with something small, and don't dedicate much time to it, just to get an idea. And then after that, you can take more precise decisions. Like, okay, it took us this, we bumped into this problem we didn't foresee. We want to do, it takes this much time per data example we want to have. It takes this much time for us to label the data. So in general, to have this much data, we have to dedicate this much time and resources. And then there's all of these other problems. I mean, where in general, we don't want the data to be biased, so that all of the different classes are evenly distributed inside of my data, and all of this. So I'm going to go deeper into this further on with some examples, but for now I'm just going to move on here with the different types of, with the different steps. Next step would be to design a model. And here, as we're using deep learning so much, one of the first questions we have to do is, do we need a deep learning model, or can we use a shallow neural network? And even further, do we even need a deep learning model at all? Do we even need a neural network? Maybe we can use other machine learning algorithms that are much simpler and not as computationally expensive. Or we don't even need a machine learning model at all. We can use other algorithms that exist. So the idea here is you don't have to reinvent the wheel. And sometimes your final application, sometimes it needs several steps. Sometimes you can do an end-to-end model where the model basically does everything for you from start to finish. But sometimes you have to divide the model into different steps. And this is also part of designing the model. So in this voice example, maybe from the start, you don't... If you have to, let's say, just for example, detect an activation word, like activate or something, then the model for activating this, for recognizing this word, this activation word, it might be a deep learning model, but you don't need to be listening all the time if somebody is saying this, because much of the time maybe the room is quiet, or most of the time we're talking about other stuff. So we can use a much simpler model, another algorithm, and we're going to see this for the facial key point detector. We can use another algorithm first to get what we need in order to use our actual deep learning model. So basically, tip here is don't reinvent the wheel, and we don't always have to go with the very complex. It tends to happen a lot in the industry right now, that some people go straight into a deep learning model when they can use a much simpler model. Fourth step is actually training your model. And here we have to make a lot of decisions, like the ones we mentioned earlier: optimizers, hyperparameters, how much time we're going to train the model and everything. We're going to look into that a bit further down. Testing your model. Here is where we add the validation and test sets. Most of you, I hope you know what those means. If not, you can just shoot me a question on Slack and we can go through that together. But you should, all of you should be familiar with what the validation and test sets are. And basically the purpose of these is to direct your work. I mean, it's not just something fancy that we use to tell other people how accurate or how good our model is. It actually gives us a footprint or a map on how we can move in terms of our project and how we can invest our resources and our time better. That's what we do with this, with the validation and the test set. And basically, just so you know, these two should come from the same distribution. Both the validation set and the test set should come from the same distribution, and it should reflect the data you expect to get in the future when you're using the model in production. So basically, it should be like a proxy of what you're going to use in the real world when you deploy the model. And the reason why both of these should be from the same distribution is because normally, if you look at the model and you're having a very low training error, but you're getting a high validation error, you usually say that you're overfitting. But if the data is not from the same distribution, if the validation and test data are from different distributions, then you can't actually make this conclusion, because you could be bumping into other problems. Other possible problems are that the test set is actually harder than the validation set. So you could be you could have deployed your model on an app, and suddenly the images that people take with their phone are much blurrier or bad quality or worse quality than the data you used when you trained in your validation set and in your training set. So being this much more difficult, no matter what you do in your validation set, it will be very difficult to know how to improve in your test set, because it's simply different. And in some cases, it's not harder, it's just different. And this is also a problem, because we're trying to improve the model by looking at our performance on the validation set, and we end up just wasting our time because the test set and the data we're going to use in production is simply different. So you don't even know what to improve to get a better performance in production. You're just focusing on this distribution that you're using for your validation. So if you don't want to bump into all of these questions, make sure that they're from the same distribution. That way, if you have a high validation error and a low testing error, then you can directly almost say, okay, we're overfitting and we're not having any of these other problems. Deployment, usual questions are if we want to have it on the edge or in the cloud. Edge, sometimes it's a bit easier for the client or something, better privacy and everything. But cloud gives us better capabilities of maintaining our model, improving it, and understanding if something is wrong. So there are pros and cons. Usually as a company, we would prefer to have these models on the cloud, deployed on the cloud, but sometimes it becomes a bit difficult to do this, and we end up being in working on the edge. Just give me 1 second here. Okay, so moving on, another step is monitoring, constantly monitoring our data. This quality assurance, it actually goes from testing the model all the way to monitoring over and over again. So people from programming backgrounds and everything, you're basically kind of familiar with this, or you should be familiar with quality assurance. And basically, training your model is a very iterative process. We have to cycle through different steps: idea, code, experiment, and we do it fast and over and over again. It's very rare that we actually get this working right from the start. It's very rare that we train a model and the first model we train that it's perfect. That basically never happens. So we have an idea, we code it up, we try it out, and if it doesn't work, we just improve the model. So I've been talking with some of you students about the debugging process, working with IDEs and all of these different things. Here, we usually do debugging while we try out different things. So the basic debugging process is in the Jupyter notebooks when we try out the different ideas. So that's at least how I do it, and how some of the teams I know work like this as well. So going on to a first example to make all of this a bit clearer, I mean all of these steps that I just went through is the day and night classifier that you worked on in the first lessons of the class. This would basically be me. I mean, what we're going to do now is basically I'm going to ask you for these different steps, and I'm going to give you a few seconds to think about it, and then we'll just go through this together in order for you to build up kind of an intuition. So I'm going to open up this cell here and basically write in a few comments as we go along. So first thing is, how would you define the problem or the goal of the day and night classifier? I'll give you a couple of seconds. Okay, so one way we could do this is given an image, or I'll write it down as like this. Classify any image. Okay, caps lock, sorry for that. Classify any image as taken. Okay, I don't know why it comes out as caps lock, but okay, I'll just go with it. Classified any image as taken during the day, and I'll set this as 1, or during the night, 0. Okay, so this is one way you could write this down, and this has several implications because now when we're going to get the data, we have to ask ourselves, what is it we want to do? And here I wrote down classify any image as taken during the day or during the night. So when we want to collect the data, we have to take this into account, because we worked with outside images in the classroom. But if we want to be able to classify any image, then we want to use indoor images as well. And indoor images are usually a bit harder, because just like you saw when I started this webinar out, I have curtains behind me. So the curtains could be blocking out some of the sunlight, and it looks darker than it actually is. And other problems we might bump into is dawn, or when the sun is coming up in the morning. These are quite difficult also to classify. So when we collect our data, we would be thinking about, okay, we can't only do this for outside images. We have to, and normal, right, 10 in the morning and 12 at night, or 12 noon and midnight. But we would have to take all of these other edge cases into account. Instead, if I change the problem and I say, okay, no, I only need outside images, this changes the way we collect the data. And a rule of thumb here in terms of the number of examples you need, because this is another question you have to think about. How much data do we have to collect? And a rule of thumb here, this is very difficult to answer because every machine learning and every deep learning problem is different. So a rule of thumb here, and I know for you guys starting off, it's not a super useful answer, but basically a rule of thumb here is compare it with other problems that you've worked on and the other similar problems, and basically think of the problem you're working on. So if we compare this to the this new problem, which is classify any image as taken during the day or during the night, and we compare it to the problem we had in the lesson, which was just outdoors images. In that case, we used 200 RGB images, and basically, I think most of you got a pretty okay model with just 200 images. So you might think, okay, this one's a bit harder, and there are other cases we have to look into. So we might have to bump it up to 1,000 or 2,000 or maybe even more. Just you can compare it to other problems you've been working on and kind of start from there. And as I mentioned earlier, sometimes just start quick, 1 or 2 days, see how you're doing, and from that make the decisions of where you're going to go in the future. Another question about the data is, in this case, we're working with images, and that comes right straight off from the problem statement. We're going to work with images. Another question that we have is, in this case, if we're working with images, which resolution are we going to work with? I'm going to give you a couple of seconds to think about that as well. So, we're working on this problem. Please give me a resolution for our images. Okay, so answering this, I would just give you this rule of thumb as well. As low resolution as possible. And yeah, I mean, it's not a super straightforward answer, but a way you can compare this is by using human performance. So I'll add it here as this. And compare it to human performance, basically. So you take as small pictures as you can, and you check with a human classifier, a person, and see how well he can do in comparing these images and getting a perfect score on the images. And I don't. Some of you maybe saw the previous webinar when I talked about the HOG classifier. I mentioned there that the HOG classifier, it divides the images into 8x8 sections, pixels of 8x8. And the reason they did this when they originally designed the HOG detector was because 8x8 was the smallest section they could use to actually get relevant features out of the image of people, because it was designed for pedestrian detection. So those 8x8 sections were the smallest they could use to get these features. So if you want to classify something like dog breeds, then if you use a 32x32 image, that might be too small, because some of these dogs, they look very similar. So it would be very hard for a human as well to be able to classify the images. So in this case, it would be better to simply use a bit of a larger image. So basically here, as small as low as possible and compared to human performance. Train design the model, and when we design the model, we get all of these, okay, all of these questions as well. It's how we're going to load the images or the data into the model. What are we going to do in our output? What kind of layers are we going to use? What kind of activation functions are we going to use? So in this case, you have the problem or the problem definition there. Which activation function would you use for the output? I'll give you 3 seconds for that as well. And if you said sigmoid function, that would be perfect, perfect activation function for this particular problem, because it's a binary problem. You want either 1 or 0, and the sigmoid function it outputs, it squashes basically the output of the model into the range of 0 and 1, and that way, if we use the logistic loss in this case, we can push the predictions to 0 or 1 in order to improve the model. So there you have a sigmoid activation function and a logistic loss for the cost function. And you have to choose the architecture as well. Do you think a deep learning model would be necessary, or what would you use? Give you a couple of seconds to think about that as well. So basically, yeah, you could use a deep learning model, but in this case, if you compare it to the project we did in the lesson, you didn't even use the neural networks. You just created a very basic, naive classifier based on the value channel of the HSV color space. So by using this, you can basically now say, okay, I might be able to do an okay classifier network with just a shallow network. So that would be perfect here as well. We could go with a shallow network, sigmoid activation, and logistic loss. And then we would have to train the model and everything, epochs and everything. That's something we're going to skip for now. I'm going to mention some of the rules of thumb or guiding rules for this in later down in the webinar. But so we'll jump into the second question, the second example we have, which is related to the project, and this is the facial key points classifier. As you can see here, this is what we want to do. We have an image, and we want to find the key points. So I basically kind of already gave you the problem definition there. Basically, given an image of a face, detect the XY coordinates of the 68 facial key points. And I want to see if you saw what I did there. Compare the two statements I just gave you for a second. The first one was simply find key points, and the second one was given an image of a face, detect the XY coordinates of the 68 facial key points. So this second phrase, it tells us how many key points there are, what we're interested in finding, which are the XY coordinates, and what we are using as input, which is an image of a face. Without this information, we might it becomes difficult to know, okay, so how do we know where the key point is? I mean, you have worked on this problem now, you should have worked on this or starting to work on this, so you know that you find them with the XY coordinates. But if you're just starting off and you don't even know that pixels, that you can divide an image and find each pixel by its XY coordinate, it can be a bit difficult for you to know how you're going to find the key points. And you don't even need the XY coordinates, because you can which are the Cartesian coordinates. You could be looking for the polar coordinates. So we're defining that we just want the XY coordinates of the 68 facial key points. That would be the problem or the goal. I'm going to leave this one empty, open for you to fill in if you want to afterwards. But basically here, in terms of the data, it's collected for us, which is 5,770 images. But as you can see, now we compare it with the previous problem and the previous two problems. We created a classifier, a simple day and night classifier with 200 images. We created, we maybe worked on a more complex day and night classifier with 1,000 images or 800 images, whatever. And in this case, this problem seems much more difficult. So yeah, we need much more data. Right now we have up to almost 6,000, and if we use data augmentation, we can have twice, 3 times or 4 times that amount of data, like 15,000 or 20,000 examples. And how we design the model also takes into account this problem definition. So if I tell you that we have to find the XY coordinates, how do you think you build your loss function? How do you build the output of your neural network? I'm not going to answer these right away. I know it's not a super difficult question, but I'm leaving it there hanging in the air for you that still haven't submitted this project or maybe haven't built the model yet. That's why I'm not actually giving any of these answers quite yet. It's just asking the questions. And you can go through the example of what we did here with the classifier and think about these different questions we have when we create models. Next question here is basically, how do you tackle your project? And I'll be basically focusing on this facial key point detector problem, but this is super general as well. I'm not showing you any of the code and of the solutions. I have the notebooks here open, which we can go through now in a few minutes. But just when you jump into the project, once you're inside, once you have defined the problem and the goal, now that you have your data, which this project gives you basically from the start, how do you design your model and how do you train your model? I'm going to add that as well. How do you train your model? That's what we're going to look into right now. And that's this, how to tackle your project. And basically, I recommend, and it's not just me, other experts in the field, many of the experts in the field, they recommend that you build your first system quickly and start iterating over that. Don't start right away with a super deep convolutional neural net, trying out capsule networks, joining different architectures together. Just start simple. Start one hidden layer. You can start with one hidden layer and just start training. And that at least that shows you, first thing you have to answer is my model, is my pipeline working correctly? Is the model able to load the data, get it into the model, calculate an output, and calculate the loss and update the weights? This super simple model will obviously be underfitting. It will have a very large bias, but it answers the first question you need to answer, which is it training at least? Is the pipeline working? And once you start from there, all of the things we've seen up until now will guide your decisions from there on. So 2 super useful tips to guide your path is error analysis and comparing the bias versus the variance and the optimal error rate. And the optimal error rate, I don't know if you've seen this in the lesson, in the classroom lessons. I'm going to share this with you now because it's super useful when you're working on your projects. I'm just checking here the chats if somebody has written something, but I don't think so. It doesn't seem like that. And it seems like everything's working all right. Okay. Perfect. So Moving on to this part, you listened to me, created your first system, you didn't dedicate much time, and now you're ready to make decisions according to what you're working with. So before jumping into these error analysis and comparing variance, bias and variance methods or tools that you may have, I just want to mention this again. When you design your model, you do not have to reinvent the wheel. There are so many papers out there, and there's so many people doing research in different areas. You can basically find awesome research in audio models, working with audio, video, images, texts, structured data, unstructured data, everything. So if you're jumping into a problem, if you jumped into the facial key point classifier detector, I don't know why I wrote classifier there. It's a detector. So if you jumped into this problem and you want to work on this, you don't have to invent the architecture from scratch. You can start by looking at other papers and what other people have been working on, and use that as your starting point after you create your first quick model. Okay, it's working. Our model with just one hidden layer is working. Let's see what's out there. We go through several papers. We find a few papers related to this project. They're maybe not exact the same project, but they're similar or related fields. And we go through the papers and we see what they tried out. We see which problems they had. We see how they fixed those problems. We see which problems they haven't been able to solve yet, and we try out their solutions for the problem we're working on, or similar problems we're working on. So, for example, if you want to have a deep learning model that basically takes in images from the front of the car and predicts the steering angle of the car, the direction the car should drive in, then that can be a pretty daunting task if you start out from scratch. But if you Google and look around online, you'll find that NVIDIA has a very good paper on end-to-end deep learning for self-driving cars. And in that paper, they have basically a neural network architecture that they used on real self-driving cars and got good results with. So you can start with that as well. And then after you try your first types of models, you do error analysis, and you can compare bias versus variance and the optimal error rate. So first of all, error analysis. What is this? Error analysis is basically the process of examining the validation set and look at which images your algorithm classified. Basically, you train the model, you make the predictions, you look at the accuracy, and or the error in this case, because we're working on a regression problem, and you see that the mean squared error here is it's not what we expected. So it's not exactly what we expected. So in this sense, how can we? What we do here in error analysis is that we look up the images with the highest error in terms of regression, or if we're classifying, we see the misclassified images, and we manually look at them. And why do we do that? I'm going to give you a couple of seconds to think why this is useful and why we would do this. And in the meantime, I'm going to check Slack because I'm getting a few notifications here, so I'm going to see if there are any questions, and I'll go back while you think about that for a second. Okay, it's more specific questions about something about math and convolutional layers, so we can work about that later on. As soon as I finish the webinar, I'll start answering these questions. about the math inside the convolutional layers and the cross entropy loss. Just in terms of this. So going back to this error analysis, why is this useful? It's because it helps us understand the underlying causes of the errors that our model is doing. And we can leverage human intuition for this. If you just look at the accuracy, you simply know, okay, the model is not it's not performing as well as I expected. But I don't know why. So by doing error analysis, by actually looking at the misclassified images or the wrong images, we can get an idea of what's happening here. So if we look at the images and we see that, okay, we're having 5% of the male images are getting are incorrect. 5% of the female images are incorrect as well. Very close images, close to the face. The performance is really good. It's great. When we go out to a farther distance, the performance gets worse, very bad, and then blurry images are quite bad as well. Just a pause there. I'm just going to mention, if the questions I'm getting here were the math about the layers and the categorical cross entropy was related to what I asked earlier. I'm sorry if I didn't see it just in time. As I mentioned, the webinar has a few seconds of delay. I'll be focusing on Slack quite a bit harder right now in case some of the other questions come up here. But just wanted to say sorry if this was related to what I said earlier. And if not, we can just look at it after the webinar. So for now, going back to this, by doing this error analysis, it gives us a path on where we want to focus our resources and our effort. So male and female images are basically the same. So in this case, we could maybe think, okay, it's not something related to being male or female. It could be because of some of the these other factors, because these are not mutually exclusive in themselves. A picture can be far away in distance and male or female, and these are not mutually exclusive. But here at least we know, okay, so if I really want to improve my model, I can focus on the pictures that are farther away and try to understand why these are why the performance is worse on these compared to the close images. This seems to be the path to go. So if you're working on this project, try doing this kind of error analysis manually, and this will probably help you to not waste so much time in terms of the decisions you have to make, but it helps guide you what kind of problems to focus on. And then the other method you can use is the bias versus variance problem. So I have here a table, and it contains here the optimal error, which I chose to be the same for all of them, the training error, validation error, and the problem, what the problem is for each one of these. So I'll give you 5 seconds, think about each one of these, and you could pause right now the webinar if you're looking at this afterwards, and try to think what the problem is here in each one of these. Okay, so some of you are probably wondering what the optimal error is. And basically here, when we talk about the optimal error, is something that can also be known as the base error rate or the unavoidable bias, which is basically error that exists in a system that that is unavoidable. I mean, no matter how precise our model is, if our model is perfect, incredibly perfect, it will never be able to be better than this optimal error. And this is a theoretical error, optimal error, which we basically right now we would have to use a proxy, an approximate optimal error, because we have no way of actually knowing what the optimal error is for a specific problem. And in many cases, the proxy we use is human performance. So we start with that. We say, okay, we have a problem, and starting off, what is the human performance? It's 4.5%. Okay, so that is the optimal error we're going to use as a benchmark. And these are the training errors and the validation error. For this first example, we're basically having a training error and a validation error that are both very close to the optimal error. So basically, I would say we're not having a problem here. We're basically almost near the optimal error, and our model is performing very, very well. The second example here, we're having a very low training error, close to the optimal error, but a large validation error. And this is called high variance, because we're overfitting to the model. It's a very low training error, and the validation error gets large. So our model has a high variance, and that would be overfitting. Here we see an example where the validation error, well, it's high, but I mean it's super low compared to a training error. They're almost the same. But the training error is very far away from the optimal error. So here we have a model that is training correctly, but it's not able to actually really understand the underlying pattern that we're looking for. So it has a high bias, and we're underfitting. Now the curious thing here is that if we were to block the optimal error out, and we just look at the training error and the validation error, let's say you didn't know that these existed. This one would be equal to, I mean, if you get this right from the start, you would have no way to know that you can actually improve it all the way down to here, because the optimal error could be 13.5, and you don't know. So if you don't have an optimal error to compare with, this could seem perfect to you. But because we do have an optimal error, we know that this has a high bias problem, an underfitting problem, and we can strive to reach this. And down here, we have a high training error and a high validation, an even higher validation error. So this one has both high bias and high variance. What could be possible solutions? I'm going to mention some of these for you. Not going to spend too much time on this, but this is something things you can test out during when you're working through this Facial Keypoint project, and when you're working on real life projects as well. So if you have a high bias problem like the one here, I'm going to highlight this. If you have this problem where you have a high bias, you can try different things like increase the model size, make it more complex, more flexible, in order to be able to train better and understand the pattern better. You can also modify the input features based on the insights from the error analysis. So if you notice that your model is having a huge problem with blurry images, then you can improve the data set, or you can change your data set around a bit and change the features in order to improve this according to what you saw in these errors. You can try to reduce or eliminate regularization. So if you're using dropout, if you're using L2 regularization, L1 regularization, you can reduce these, because these are methods that you use to reduce overfitting, which is the other problem we're having. So we can reduce regularization here in order to try to reduce the bias. And we can also try to modify the model architecture. We can try a much more complex architecture. If we're having a high variance problem, which would be this one over here, a few steps you can try could be adding regularization, the opposite to what I just mentioned. You can try adding early stopping, which is usually as the model trains, it kind of converges to a point where the training error is very similar to the validation error. And if we keep training longer, then the validation error usually starts to go up. So early stopping is usually when we stop right there when the training error and the validation error are super similar. The thing is that in this case, when we use this, we're kind of checking two things at the same time. And it makes it difficult for us to know if we're actually underfitting or overfitting. So this is a good method, but I recommend using the other methods first, adding or taking away regularization, and using early stopping just as an alternative if you actually need it. You can try feature selection, decreasing the number of inputs, because if the model is too complex and your data set is too small, you might be having a problem there. But in many cases, what you should do if you have a high variance, something that almost always helps is adding more training data. So if you're having a high variance problem, I recommend adding more training data. But instead, if you have a high bias problem, adding more data usually doesn't solve this particular problem. So that's why the other methods work well. So by having an intuition on what you can do in each case, this helps you to better decide what you are going to do in each situation. That's possible solutions there. And an interesting project, if you're going to work on something, I recommend that you're at least interested in the project, or else it's kind of a headache. That it's good if you have domain knowledge, because usually this is where the biggest insights come from. I mean, if you can leverage domain knowledge for error analysis in your model, you'll usually get, and to design your model from the start, you'll usually get much better results than if you don't have domain knowledge. The utility is obviously what you can get out of creating this kind of, solving this kind of problem. The feasibility, can you get the data? Do you have the resources to train and everything? Here in data availability, a good thing to look for is, can a human do this problem well? So here I'm not just talking about the facial key point project, but any project. If you're thinking about doing a project, try checking these off, and this makes the whole process a bit easier. Why ask yourself if a human can do this well? Because one, it's easier to obtain data from human labelers. They label the data for you. So if a human doesn't do this well at all, it gets kind of hard to get the data to do a supervised learning, to solve it with a supervised learning method. You can use error analysis to draw from the human intuition, and you can use the human level performance to estimate the optimal error rate. So all of these are benefits that you get from trying to get a problem that a human can do well. And here I added a few resources. If you want to know the difference between the different optimizers, I mean, this one is super in-depth, but it's one of the best ways to actually know the difference between each type of optimizer. And if you want to have an intuition on how they work, FastAI, the FastAI course has some very good videos on optimizers as well. If you want to augment your data, if you want to rotate the images or something, this is definitely something you can look into. If you want to improve the face and eye detectors, you can look at this tutorial to train a better hard cascade eye detector and face detector for your images, in case you're feeling that your detectors are not good enough. And here's a comparison of the different face detectors in the market, open source face detectors. So here we're using a HAR cascade-based face detector in this project. A model that usually works very well, which is part of the OpenCV library, is a deep neural network-based face detector, which you can also use often in real time with the CPU and everything. So you can see this comparison over here. And that's basically kind of the most of the content I had for the webinar today. about doing and how to work and tackle a machine learning project in the real world. I hope this was useful for you and that you can use these recommendations on error analysis and bias and variance studies comparing with the optimal error rate to work on your project and to know what to change as you're going along. If you need a deeper model, a more shallow model, more data through data augmentation, if you need to add dropout or reduce dropouts, all of these are decisions you can make after using these tools. So, and as you can see, let's go through if there's anything here in the projects. Importing at the top, as I have recommended. There's no solution code here. You can see that I'm looking at this straight from the GitHub. So you can jump out from the webinar right now. Most of the actual content, which was about doing machine learning projects, I've mentioned that now. I'm just going to go do a quick I'm going to look quickly at the different notebooks and see if and mention any things that people have asked me. So people that are not really familiarized with Python, we create objects, and here we define a class, which is a data set, and these kind of things, they're super interesting and useful parts, kind of tools we have in the Python language. So this underscore init _ is basically what we call constructors in other programming languages, and it is automatically called when an object of this class is created. So basically, we're creating a class here, and then we want to create an object or an instance of this class. This function here, basically, this gets called automatically. And what it does is that it fills in these attributes basically with this information, which is something that you give the class when you create the instance. Here, len basically allows you to give a length of this object and so on. So these are things you can look up online, but super useful, and that's basically what this does. This is a constructor. Going through down here, transforms. So here, normalizing, we do this because this usually helps the model to generalize better right from the start. It helps learning. It makes learning much faster because if we have numbers and I mean, if each input value is kind of 1,000, 1,200, 200, I mean 255 here in terms of images, we can end up with something called exploding gradients in the network. So you can Google that if you're interested about knowing what that is. But just simply keeping them small, between 0 and 1, makes it much easier for the model to learn right from the start. And even the range from -1 to 1. Both of those makes it much easier. Here, rescaling and random cropping. Rescaling, it often happens that neural networks, when we use transfer learning, these architectures, they have a specific size that they expect the images to be in. That's usually in PyTorch for the models we're working with. That's usually 224 by 224. So we want to use these two methods to get the images into the right sizes. And random crop is a way of also augmenting our data by each time cropping a different part, cropping the images with different sizes. So sometimes it's a bit more zoomed in, sometimes it's a bit farther away, and this helps to augment our data. And you can add other methods here as well to augment it even more in the transformations. So done with that one. Here we define the neural network, and here's where I can tell you that you can look at papers to have something to start from, but recommendations: start small, start fast. Here is something perfect. As I just mentioned, there's a paper you can look at to see an example of a structure of a network that you can start with and use as your starting point before doing error analysis and all of this. So I super recommend that you read this paper. Here, basically, we use classes as well, I think we have here, yeah. We define these neural networks in a specific way. We can use built-in parts of the PyTorch library to make this much easier. I mean, this way we create custom neural networks, but we use existing features in the PyTorch library to make this much easier to build. Transform data set, batching and loading the data. Sometimes you can't give your model all of the data at once. That's why we create batches. And here we have applying the model on a test sample. And this has to do with what I mentioned. It's good to test your data to see how you're doing, but these test samples, they should be from the same distribution that you're using for validation and training as well. Visualizing the predicted key points just to compare what you're doing, and with this part here, you can do error analysis. I think down here or in another notebook, you basically you can see the actual labels next to the actual key points next to your predicted key points, and that's a perfect way to do error analysis as well. Here, to define the loss and optimization, you can look at the Sebastian Ruder post I added here in the end, this one. And you just start training and testing. These are questions you have to answer, and these are usually part of the rubric as well, so you have to answer these to pass the project. And these feature maps are simply useful ways for you to know what's happening inside of the neural network, because one of the critiques that neural networks often get is that they're black boxes. It's good that you're able to create these feature maps to actually explain what's happening inside of the neural net. Okay, the last network is about doing fun stuff with these key points, so I'm not going to go into that one. I'll just use the last one here. Let's see if I had anything in my notes. Okay, yeah, this is I'm going to end with this. This is exactly what I was mentioning earlier. You don't always need an end-to-end solution. Here, hard cascade classifiers, they detect the faces super easy, and I mean in a super efficient manner, fast on your CPU, a proven method. So instead of trying to figure out where the eyes are or the key points are in a large image, I mean where the face is just a small blob there in the middle, you can use the hard cascade classifier to get the coordinates of the face and then detect the key points inside of that little area. So adding this step first makes it just much easier and much faster to get the results, and improves the performance of your model. And that was basically it. Just if you have any other questions, my main focus here was trying to explain how you can use this, how you can tackle projects in real world, and just giving you guidelines that you can use while you're going through this project and the future projects in terms of determining which path to take and how to improve and how to reduce the amount of wasted time and resources. And with that, I'm going back to myself, and thank you very much for being with me. 9 minutes past the hour mark. I didn't see any more questions on Slack, and I didn't see any questions on YouTube. So that's all for today. I hope you enjoyed this webinar. When you watch it, you can, as I mentioned, watch it much faster. And I'll see you next week. For all of you who have finished the project, congratulations. You're definitely on your way. You're doing huge amounts of progress, and don't forget to set up the one-on-one calls with me weekly so we can go through your progress. And I want to thank Some of you, like Joe and Sanya, have been adding up resources to our shared resources file. So you can take a look at that anytime to see different things that can be useful for you as a computer vision engineer or practitioner. And please add more resources as well. So thank you, Joe. Thank you, Sanya. And I thank anybody else who has been adding stuff to that resources document. That's basically it. Thank you very much, and I really look forward to talking to you guys next week and for the next webinar. Bye bye.